Welcome to our balancing chemical equations video. We're going to start off with an equation that's in formula form, and then after we're going to do one that is in word form. So what we want to do is take a look at our inventory of our reactants and compare it to our products so that ultimately we sort of have the same numbers of elements, or the same proportions of the elements. So we're just going to write out a list, and however I write the list on my reactant side, I'm going to write it the exact same on my product side, just so I can compare. So I'm going to count up how many of each item we have to start. And before I start counting, I'm going to work this 3 in. And by that, I mean like we're multiplying it in. So there's a boron and 3 hydroxide ions. Each hydroxide ion's like a -1, but they must use 3 of them. So what that means is that there's 3 H's and there's 3 O's. So it's sort of like algebra where you're distributing that in. So 2 hydrogens in our first reactant, and then 3 hydrogens in our second. So we've got a total of 5 hydrogens to start off with. There's 1 sulfur, there's 4 oxygens here, and then 3, so a total of 7 oxygens, and 1 boron. So looking over on the product side, again, we're going to use this 3 and have it apply to all the elements in the sulfate ion, so that we have 12 oxygens plus 1 to make 13. We've got 3 sulfurs. There's 2 boron. We can see with the subscript there. And then the hydrogen is just sitting at a 2. Ooh, very interesting. So, what are we going to do here to start to balance these things out? And because this is trial and error, we may go down one path and then have to rebalance altogether, again. So this is, we're just trying it out and seeing what might work. So, one of the things I would be seeing here is, that there's 2 borons on this side and there's only 1 on that side, which, is a signal to me that I'm going to have to at least double this boron amount. If not, quadruple it and double this or something. So what happens when I do put 2? This 2 means this whole particle is there twice. So it's 2 full particles of the boron hydroxide. So 2 borons. The 2 starts to work inside on this. So if there was 3 oxygens originally, now there's going to be 6. 6 plus 4 makes 10. And again, there's 3 hydrogens originally. Double that to make 6. So that makes 8. So how are we doing here? Okay, very interesting. So our borons are now satisfied. The sulfur is, and I'm pinpointing those because the water is like duplicating some of the elements for us. So sulfur is like literally only in this particle, so I know that there's 3 of it. So I'm just gonna take a guess that I'm gonna need to have 3 sulfurs over on this side. So 3 times 2 makes 6 for the hydrogen. Plus I have already 6 over here, so that's 12. Again, that was 3 times 2 makes 6 hydrogens. And this is 3 hydrogens times 2 to make 6. 6 plus 6 makes 12. For the sulfur, 3 S's, perfect. And then this 3 is multiplied with the 4 to make 12 oxygens. And over here I have 6. So that's a lot of oxygens. 12 plus 6, 18. Okay, so how does this compare? So sulfur's good, boron's good. So maybe we could deal with the hydrogen here. So we need 12 on this side, 2 here. What happens, like I'm just taking a guess, what happens if we make that a 6? So 6 times the hydrogens makes 12. Great. 6 plus times 1. So 6 oxygens here. We had 12 over here. 12 plus 6, 18. Oh yeah, bingo. Right on. Excellent. So that balancing just fell into place. So once we can kind of go through and say 12, 3, 18, 2, 12, 3, 18, 2, we've got the balance on both sides of the equation, and we're done. But what I wanted to also look at is an equation that's written out, where it's our responsibility to come up with a equation and then, of course, balance it. So I like to kind of read through the question first, just verify what are reactants, what are products, because that's kind of one of our first stages is what's combining and what's being formed. So we've got potassium hydroxide, hydrogen gas are formed. So these items are formed when potassium chips react with water. Oh goodness. So potassium hydroxide and hydrogen gas are going to be our products. And potassium chips and water are going to be our reactants. So it's really key to read through for understanding, not just for detail. So, and it's all coming down to these guys being formed. Whereas you could say potassium chips and water react to form potassium hydroxide and hydrogen gas. That would be another way of saying exactly the same thing. Secondly, let's kind of start with the reactants. And some of these things here, like chips, we're going to have to infer that this means solid. So we're going to have potassium, and we're going to represent that it's in chip form or in solid form by putting a bracket and an S and a bracket down below. We want to have water, H2O. My guess is that this is not ice and this is not steam. So I think it's fair to guess that this is liquid water. Whereas it's not like a gaseous form of water or a solid form of water. So we have solid potassium reacting with liquid water to form potassium hydroxide. And, you know, sometimes people like to do a side calculation here. I myself would usually like to do it above in the question. So I'm just going to do a quick crisscross. So potassium hydroxide. And so we would have KOH. But this is unknown, you know, potassium hydroxide. It doesn't tell us what kind, like, is this a gaseous form? Is this an aqueous form? Is this a solid precipitate? We don't know. So that's okay to sort of leave that blank. But in this case here, where it has hydrogen gas, we definitely want to be representing it with the G. So one thing for sure, keep in mind that we are going to have diatomic elements. So, get any of your have no fear of ice cold beer, or I have no bright or clever friends. It's not a very nice one, but they all indicate our diatomic elements. So watch out for nitrogen gas, chlorine gas, hydrogen gas, you know what I'm talking about. So in that sense here, super important to represent hydrogen with a 2 in the subscript. It absolutely cannot be just a straight up H. So we're looking through to see if there's any need for balancing, and there's 1K here, 1K here, 1 oxygen here, 1 oxygen here, 2 hydrogens here, 2 hydrogens here, and 1 over here. Oh, drat. This is tricky. So I think, at this point we can kind of start to work maybe with this mentally, but it's not such a bad idea to just write down our inventory so that we can get a sense of where we're at. So the problem's lying with the hydrogen, and it's probably best to take this odd number and make it even at this point, because this is only ever going to be an even number. It's only going to ever be 2 or 4 or 6 or 8. So we can never really get 5, for example. So let's at least double this. So the effect of doubling this. So 2 hydrogens plus those 2 make 4 hydrogens altogether. And then now to react to that, I need to now double my potassium. I've doubled my oxygen, so I'm definitely going to need to do that. And now I've effectively balanced out the hydrogens. So in terms of double checking through a question like this, you want to make sure that there's as many states as possible written down here. My feeling about this, if I had to guess, is that that's an aqueous potassium hydroxide. It doesn't say that, but when you take potassium and you put it in water, then you're creating that aqueous solution. So these are your 4 states of matter, whereas where aqueous is just showing that they're going to be within solution, a water-based solution, but in ion form.